that we can switch off interaction between the electrons, setting this lambda constant to 0. So lambda scales electron-electron interaction, 1 over R12 term in the Hamiltonian. Well, in this case, of course, we will have non-interacting particles. I don't care at this moment about the external potential. I assume that it can always be found, because I know that for ensemble density, it does exist. However, in this case, I have a system, ensemble system, where two fractionally occupied orbitals are degenerate. And they are occupied with some fractional number of electrons, Na and Nb, for each of them. What I can do now, let increase infinitesimally the lambda scaling constant, just by a tiny fraction, such that only electrons in the degenerate orbitals will feel this Coulomb repulsion, or I mean Coulomb repulsion between the electrons, and the electrons in core orbitals. There may be many more electrons in the core orbitals, which are non-degenerate. They will not feel this Coulomb repulsion. You see, when two orbitals or two states are degenerate, then any even infinitesimal coupling between them can lift the degeneracy, right? And that's what I would be interested in to construct the functional for ensemble density. Right, at this infinitesimal lambda, non-zero but very small, I apply quasi-degenerate perturbation theory. I build a simple 2x2 secular problem. I solve it in the same way as I shown before, expressing energy of ensemble state through energies of individual ensemble components. So these are energies of individual ensemble components, and this is the coupling term. In the limit of strictly non-interacting electrons, this term will vanish, because this energy will become equal to that energy. Broken symmetry becomes equal to triplet if lambda is 0. And therefore, I end up with a strict ensemble representation of the energy of the non-interacting electrons. Then I take this energy expression, apply lambda integration, or integration with respect to electron-electron coupling strength, this constant, from 0 to 1. At the formal level, this can be done. And I end up with this simple energy expression, where instead of energies of non-interacting particles at lambda near 0, at this value of lambda, I have density functional expressions of these same energies of the same configurations with lambda equals 1. So fully interacting particles, but I have now fractional orbital occupations of these two orbitals in the ensemble configuration. So from here to there, I go by lambda integration, and this can be done, as is explained in a couple of the next slides, but I will not explain it in detail because it's too much, let's say, derivations. I will go to the next slide immediately. So I can obtain, for example, for the case of a strongly correlated system where I need to have ensemble representation for the density, I have the energy expressed in this way, right? However, for weak non-dynamic correlation or no non-dynamic correlation at all, I need to recover the same energy expression as in the case of standard Kohn-Sham theory. So, and the trick that I use in the derivation of my method was to interpolate between the two limits, limit of strong non-dynamic correlation, where both orbitals are, say, almost equally or exactly equally occupied, this limit, and limit of normal Kohn-Sham system, which is dominated by the dynamic electron correlation only. So as a matter of fact, for standard Kohn-Sham methodology, around these two occupation numbers of some frontier Kohn-Sham orbitals, let it be HOMO, let it be LUMO, highest occupied molecular orbital, lowest occupied molecular orbital in the standard description, I can obtain this expression with delta, which is almost the same as the exchange integral here, but only in front of it, there will be a linear term in the product of the occupation numbers of these two orbitals, and it will vanish in the case of Na2 and B0. But this one is square root of the two. So I introduce simple interpolating function, like it is shown here, between the two limits. And there are some kind of parameter delta was chosen to provide for smooth dependence of the variationally obtained occupation number, for example, one of the components of the ensemble, with respect to the magnitude of this term, delta. All right, so this is a non-empirical expression, maybe not exact, but our DFT is not exact either. And in the end, everything boils down to quite simple. For the case of two electrons in two active orbitals, this leads to ensemble with only two components. I have two quasi-degenerate, nearly degenerate orbitals A and B. All other orbitals are doubly occupied. I will have two configurations with doubly occupied orbital A with doubly occupied orbital B. They will make these contributions into the total density. So densities of these configurations will be combined with these weights. And I will end up with fractional occupations of frontier orbitals A and B. And the energy expression will have, again, two energies of the two ensemble components, which is the same, plus some term which describes coupling between the two components. So the formal level, at the level of in the limit of non-interacting particles, the two become the same. So this term vanishes and the two become the same, very similar expressions with rho and E as it should be. But in the limit of, say, fully interacting particles, I will have some contributions from interaction, from coupling between these ensemble components. So then what I do, I optimize this energy variationally with respect to the orbitals, all these orbitals, not only active, but also core orbitals, and with respect to the fractional occupation numbers. So simultaneous optimization with respect to orbitals and fractional occupation numbers. So formality, I use OpenShell SCF for that case. For optimizing occupation numbers, well, it's easy problem. I eliminate one of them by constraint that I should have two electrons within the active subspace. And then I optimize the expression with respect to the orbitals under constraint of orbital orthonormality. And this leads to OpenShell methodology, which is quite tedious. I will not explain all of it. I will only mention that what you will see as after the SCF cycles, as the orbital energies are not exactly the orbital energies. They can be arbitrary, the diagonal elements. What is important that the off-diagonal elements become zero at the convergence. So, and to obtain energies of orbitals, which we use to associate with the ionization potentials, electron affinities, we can use a different trick. But the machinery, which is outlined here, is not really important. What's important is that this is OpenShell SCF methodology. And in this SCF methodology, when I impose this orthonormality constraint, Lagrangian constraint, the matrix of Lagrangian multipliers, which can always be made diagonal in the case of closed shell Kohn-Sham systems, right? Standard Kohn-Sham single determinant, it cannot be made diagonal here. It should become symmetric, the matrix of Lagrange multipliers, but diagonal it cannot be made, because otherwise we would mix orbitals with different occupations. And this is one important difference between open shell SCF methodology and closed shell SCF methodology. So one is that the diagonal elements of the Fock operator are not exactly the same as in, or the interpretation is not exactly the same as in the closed shell and the case. And the other is that the off-diagonal Lagrangian multipliers, elements of the Fock matrix, in other words, they do not vanish strictly. So this is, say, Fock matrix which is diagonalizable, but in reality, these Lagrangian multipliers,
your Fock size is twice as big as normal Fock, right?
No, it's not twice as big. The dimension remains the same, only that I need to combine Fock operators of several electronic configurations when building it. So I build this Fock matrix from Fock matrices of individual electronic configurations, like shown here. Electronic configuration corresponding to W-occupied orbital A, W-occupied orbital B, and all these intermediates. Broken symmetry, AB, BA, and a high spin, both spins.
Oh, you sort of Fock is a linear combination then.
Right, yes, that's linear combination of, well, these and that are equal, Fock operators equal energy. I only write them for completeness, and this and that are also equal, and therefore I have 4 different Fock matrices to combine into one. So roughly speaking, this is 4 times more difficult than to calculate the Fock matrix of standard closed shell system.
So in your case, the interpolation you said, which is the kind of adiabatic connection, intermediate adiabatic connection, or variable adiabatic connection, right?
Yes, in some sense, one can say that. Yeah, this is, I want to interpolate between the limits of the, say, strong non-dynamic correlation, say maximally strong, which leads to equal occupation numbers of orbitals A and B, 1 and 1, and the limit of very weak or negligible non-dynamic correlation, where an A becomes 2 and B 0. So that was important for eliminating any, let's say, double counting. I can show it in some examples. So all this scheme was implemented in computer programs. In the very beginning, we used some now obscure code named CatPack. Later, I used Gaussian. Later, I did it in TerraCam, and now I did it in games.
Games.
Yeah. And, well, say applications are...
Say here, spin restricted here.
Right. Spin restriction is due to, well, orbitals for alpha and beta spins are the same. Space orbitals, I mean, special parts of the orbitals are the same. I didn't want, well, if I wanted to use, let's say, spin unrestricted, I would need to handle with, say, different orbitals for alpha and beta spins.
Yeah, that would be further more complicated, right? So.
It would be more complicated computationally, yes. I'm not sure that it would be really more complicated at the formal level, but in principle, it could be, well...
You just need more calculations for different orbitals.
Yes, right. That would be 6 times cost of the UHF calculation, because I would need them all. In that case, I suppose.
Yeah.
The cost calculation of the calculation would increase, simply speaking.
Okay.
So, and I can in the following show some applications for the ground state.
By the way, sorry, we need to limit the time. So
yeah, we have already half an hour.
So maybe we should finish it soon.
Yeah. I will. I think that I have maybe about 10 slides remaining, which are quite simple to show.
And then
so one of interesting
10 more is too much. I think that Anna wants to talk. Give a question.
Right.
Yes, actually, I didn't understand fully. So you for the particular system you calculate the this f function. So that interpolation function.
Yeah.
Yeah, and for each particular, it is different for each particular system. Yes,
No,
is
no,
this
no.
true?
It's
No.
all the same for all systems. It's
You just obtain it for one function that's obtained
right.
for and use it for
Yes.
for
I use
and
it for,
well, I see delta is 0.4. Yeah, it is.
yeah. Yes.
Yeah, you find it for. It depends on what your correlation.
It is shown in this graph. Let me tell you. If I set delta to 0 strictly, then there will be no unique solution for the given energy difference between the well, this parameter here, capital delta, abscissa axis, characterizes energy difference between the two electronic configurations, W occupied A, W occupied B orbital, divided by the coupling term. So this is the same parameter as in inverted parameter as in the perturbation theory, right? So 0 would correspond to say degenerate configurations, and non-zero would correspond to non-degenerate. So they are negative, these parameters, as a matter of fact. All right. If I set this small delta to 0, I obtain non-unique solutions for the occupation number of fractional occupation number of the orbitals, because there will be an artificial solution corresponding to some intermediate, and there will be very non-smooth dependence of this occupation number. In fact, both occupation numbers on these.
So what is the reason you choose 0.4? Is that
if I use with delta 0.1, it's smoother and it's unique solutions, but it's not really smooth. There is kind of kink at this point. Delta, if I gradually increase delta any further, I see that starting from delta approximately 0.4, I increase them in fixed steps, 0.1, 0.2, 0.3 I don't show because they are very close, but I see that they gradually converge, and if I go beyond delta 0.4, they all remain these curves, the dependence of variationally optimized fractional occupation number on this parameter, which is the most important for the magnitude of correlation. I see that they all converge to the same dependence. You can probably, delta 0.5 is very indistinguishable from delta 0.4. 0.6 would be also very close. So they
but it's okay. But do you obtain this number from some particular computation or for some particular system, or you?
No, this is not for any particular system, because
not for
this parameter is. You see, when I optimize that, all right, where did I put optimization formally? All right, it doesn't matter. I can optimize by Newton-Raphson method. When I know energies of all these components of the ensemble, right? I optimize for.
So it is in common case. It is just a theory, yes. And you did not apply any specific DFT correlation potential, yeah. DFT functional, yeah. It is for any functional, yes.
Right. I did not apply any because I think I was testing my Newton-Raphson optimizer for these fractional orbital occupations. And I found out that the value of this depends on this parameter, capital delta. Well, and then knowing this, it's quite non-linear dependence, in fact. But knowing this, I can find always this orbital occupation number, fractional occupation number. And as a matter of fact, that Newton-Raphson procedure, it would converge to say non-unique solution if I set small delta to 0 to a non-smooth curve, non-smooth solution, if I set too small delta, but it starts rapidly converging to one and the same dependence, starting approximately from delta equals 0.4. I did not try to find any, say, refined value of these. Simply.
So, and it is affect only Coulomb interactions, yes?
Right. This is largely defined by these parameters or ratio of the average of the, difference of the two energies and the coupling term.
Okay, so
nothing else.
This is good point to stop. Okay, so we'll continue from here. Yeah, okay, Pavel, yeah. Pavel, you have a question?
Actually, I have a lot of questions.
Okay. One question.
One question. Actually, I'm going to just make a talk about the quantum materials next Monday, actually. And I suppose that the ensemble DFT may be the best method to apply for them. And I'm going to discuss it. Actually, it's incredibly important for quantum materials. No way to model such sort of materials by using just ordinary, regular DFT or something like this. I'm going to talk about it next
one day. Yeah, we were looking for it.
Incredibly important.
Yeah.
Actually, I promise you that for me it will take not more than 60 minutes.
Okay, you don't have to, but okay, so maybe I wasn't really properly preparing Michael's talks because I didn't know where to stop. So, but then anyway, I have to stop. Saima, you recorded everything, right?
One last slide I would like to show before we stop.
All right.
About that interpolating function, that it is important to correctly describe the energy at the, say, equilibrium conformation. For example, a hydrogen molecule, as you see, the dissociation curve obtained from REKS 2,2 and from standard Kohn-Sham, they go to different dissociation limits. Of course, REKS goes to proper dissociation limit, -1 atomic unit, Hartree. But near the equilibrium geometry, both curves are the same, and the energies from REKS and from standard single reference DFT are also the same. And here, the electronic structure is dominated by single electronic configuration and mostly dynamic correlation. So this means that REKS does not introduce any, say, any extra contribution into the standard Kohn-Sham description, provided that Kohn-Sham description is valid. And the same I observe also for twisting about the double bond in ethylene molecule, where at planar conformation, I obtain the same energy as from the standard single reference Kohn-Sham, although at 90 degrees twisted.
Yeah. Okay, so we'll talk about tomorrow, all right?
That will be tomorrow.
Yeah. That will
and
be...
also excited states will
be...
yeah,
okay.